Hi everyone, I'm Rose Hoffman and I'll be walking you through problem number 7 from section 3.1. So this problem, the goal of this problem is to find the power series solution and identify it in terms of a familiar function. And then once we do that, we are going to determine the radius of convergence. So I wrote down our given equation up here. So 2x minus 1, that quantity times y prime plus 2y is equal to 0. So in the first step, I let y equal that series, and the reason I did that was so that we could find some expressions that we will use to substitute back into our original function. So I let y equal the series from n equals 0 to infinity times cn times x to the n. And then I took the derivative of that to find y prime, and that series looks like this here. So it's n equals 1 to infinity times n times c to the n minus 1 times x to the n minus 1. And all of these n minus 1s come from when you take the derivative, you subtract 1 from the exponent. So once I have both the y and y prime, I substituted those back in for my original function. And this function here, I just expanded this a little bit. So it now is 2xy prime minus y prime plus 2y equals 0. Alright, so putting in those two expressions from above, I have this line here. This is 2 times that y prime times x minus the y prime again, plus 2 times our y function, and set that all equal to 0. Now I took this little piece here and I just simplified a little bit. So I'm looking at this x term and this x term. When you multiply both of those together, you can just add the exponents. So n minus 1 plus 1 is what leaves me with this x to the n term. So I just carry down these other two here, and that's how I got that final line there. So step number 3, I am going to use a dummy variable to help us solve this. So I let k equal n minus 1, so therefore n equals k plus 1. So I just substituted the k plus 1 in for all of my n's from right here. So doing that, here, this one just carried right down, and same as this one is carried down. But this one was substituted, so starting here, minus the series k equals 0 to infinity times k plus 1 times c to the k plus 1 times x to the k. And now I substituted n back in for k. It doesn't really matter what variable you use, but I just use n since all of our other variables are n's. So doing that, you'll have, again, your n plus 1 times c to the n plus 1 times x to the n. And again, the other two terms just carry down, and that entire thing I set equal to 0. Now I just factored out some common factors, so that series and this x to the n. So in here, it's the series from n equals 0 to infinity of the quantity 2n cn minus n plus 1 times c to the n plus 1 plus 2 times cn, and that entire quantity times x to the n, and that is all again set equal to 0. So after all of that work and all those steps, we can now use this information in the middle here along with the identity principle from right here, and that's just going to say we can set all those coefficients equal to 0. So the goal of this, we want to find what our c to the n plus 1 is equal to. So beginning here, I have my 2n c to the n minus n plus 1 times c to the n plus 1 plus 2 c to the n, and again, that's all set equal to 0. The next step here is just some simplifying. I factored out 2 to the n plus 1 from my cn, and then I added this n plus 1 times c to the n plus 1 to the other side, and then dividing both sides by n plus 1 will leave me with c to the n plus 1 equal to 2cn. So that is our, this is what we need to continue solving our problem. Alright, so continuing on, once I found how c to the n plus 1 and 2cn were related, I then plugged in some values for n just to generate some terms in our series. So when I plugged in n equals 0, I got c to the n, so c to 0 plus 1 is c to the 1, equals 2 times c to the 0. And then plugged in 1 and did the same thing, but in this case I got c2 is equal to 2c1, And we actually found C1 up here, so then I just plugged in 2 times 2 times C naught equals 4 C naught. And that same pattern continues all the way down here. So I just wrote my result over on the right hand side here, and those are the first few terms in that series. So going back to what we had on the first page here, when I let y equal this series. So if I let y equal this series, if I just generated the first few terms of this series, this is what I'll get. So I just took my coefficient values that I found up above here and just plugged it in for what this series is supposed to look like. So plugging in those coefficients, I'll get Cn equals C naught plus 2 C naught x plus 4 C naught x squared plus 8 C naught x cubed plus 16 C naught x to the fourth, and that just continues on and on for however many terms you want in that series. I just factored out in this next part the C naught, so I can try to discover what the pattern is. So 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the fourth. And then to make it even easier to look at, I noticed that all of these terms were powers of 2. So I just rewrote that entire series again with powers of 2. So I have C naught equals 2 to the 0 plus 2 to the 1 times x plus 2 squared times x squared plus 2 cubed times x cubed plus 2 to the fourth times x to the fourth. So seeing this written out just like that, it was really easy to determine my Cn function. So Cn equals 2 to the n, so that's that 2 to the power times this C naught out in front times this x to the n, x to the n, x to the n. So this is what my power series, or this is my solution to the power series. Now in this problem, it wanted you to write it and identify it in terms of a familiar function. So I went ahead and looked on page 195, which has a list of all the familiar functions, and I looked down, it was near the bottom of that list, I found this one, the 1 over 1 minus x, which I believe looked very similar to my series up above. So 1 plus x squared plus x cubed. That looks exactly like ours, other than the fact that we just have powers of 2 out in front. So because we have those powers of 2 and this C naught, I took that into account to help write that function. So here's that C naught right here out in front, and then all of our powers of 2 come into play with this minus 2x term. So our final equation and solution to this series is y of x equals C naught over 1 minus 2x. So again, that is my final answer there. So that was part 1 completed. So now I just went on to part number 2, which wanted you to determine the radius of convergence. And radius of convergence is just equal to the limit of, I just use n as n approaches infinity, of this c to the n that we found up here over the next term, so c to the n plus 1. Now plugging in my values for this, see, I just took this right here, plugged that in, so I have that 2 naught C naught right there over 2 to the n plus 1 over, or that entire thing's over 2 to the n plus 1 times C naught. So this would be the next term in that series. So now from here it's just some math and using exponents to determine what our radius of convergence is. So those C naught values just canceled out right away, so didn't have to worry about those. So now I'm just looking at the limit as n approaches infinity of 2 to the n over 2 to the n plus 1. Now, like I did earlier, when you have 2n over 2n plus 1, when you have this plus term here, you can actually just multiply those. So looking down here now, so this 2 to the n plus 1, it just turns into 2n times 2, which I wrote right there. So now, and that helps us because once we have that 2n written down in the denominator, we can cancel it out with the numerator. So cancel this out, looking next here, so all I'm left with is the limit as n approaches or as n approaches infinity, of 1 over 2. So the limit of a constant is just going to be a constant, so our final answer is 1/2. So for part 2, the final answer, the radius of convergence is 1/2. So I hope that cleared up some questions for you guys. Thanks for watching.